Well, I think we can get going. Welcome back, everyone. We just got through our second exam, and I guess it's a good time to just open up the class for questions. Any questions about exam 2 that folks would like to discuss? Okay, well, we've got our summary statistics here. The average grade for the entire class came out to 83.2%. I thought that was really amazing since on exam 1, let's scroll up to that one. On exam 1, the summary statistic was 80.5% on the average. It is kind of unusual for exam 2 to actually go up, since I think it is a trickier exam. So good work on that, folks. That shows lots of extra practice and studying to get through this one. Also on the second exam, just like on the first, the solutions are posted here if you like to take a look at them. It opens up as a PDF. Summary statistics are here as well. And these are the steps that I took to solve these kinds of problems. A lot of them just have the answers because I put it in a calculator. But for the others, I try to put in as many steps and extra detail as possible for these kinds of problems. Let me take a look. Is this the right local coffee shop? Z-scores. Yeah, I believe this is, wait a minute.
That was
Spring 20, I must have uploaded the wrong set of exams. This was for the 75-minute class. Sorry about that, folks. I'll come back here and re-upload the real one, but you know what, we could just leave that there. That's how it was for spring 2023. I'll put the fall 2023 solutions right under it. I must have just kind of grabbed the wrong file off of my thumb drive and put it into Moodle. So I'll fix this one here. Let me put a note of it just to make sure. I thought it seemed a little odd. That didn't seem like the actual problems that we solved. I'll put upload correct exam 2 solutions. And what the heck, like I said, we'll leave these ones posted here, even though it wasn't our exam. This was when the class was 75 minutes long, so there's extra problems on that one. And it could be a good study resource as well when we're getting closer to the final exam. But aside from that, where we're at so far is in section 6.5, and we're actually picking up a lot of steam. It takes a while to get through the probability section, but 6.5 now connects with section 8.2. After section 8.2, we'll be in chapter 9, and we'll finally be doing a full and honest confidence interval. We're going to be dealing with proportions first, so our data is going to be categorical. We haven't looked at categorical data in quite a while, so that's probably a good idea. Then we're going to redo all of our inferential statistics with quantitative data again. So we'll be looking at means and standard deviations. So that's what we're at so far. Any questions or comments at all, folks, before we jump back to 6.5? Okay, well, if the problems we're about to solve, they're very similar to quiz number 9. Quiz number 9 is going to be dealing with the normal distribution. We have to use a calculator now to get through each one of these problems. And section 6.5, it's really kind of designed to be a one-stop shop location for how to operate the calculator for any one of these kinds of problems. So the first example up here, just to have one ready to go, is this situation. We're trying to calculate the probability that X is greater than a specific value. It was 0.1234. That made it a normal CDF problem. And all we had to do was organize the graph in this way. Then down below is the step-by-step guide on getting through it. But we didn't have quite enough time to do the step-by-step guide on this one. We did do it in the calculator, but let's slow down this time. Now we have extra time and go through it again. So this one is the inverse norm problem. What makes it an inverse norm is there was no actual value inside the probability function. Instead, we had to solve for K. And to do that, first thing we need to do is put down the graph. This is always the most critical step of this process. We put down right here where we believed K would be located. I guessed around, say, -11. Turns out it was more around this area, but that's okay. It was only for us to guess. Then we had to input in the area as our first input, the mean and the standard deviation as our second and third input. But no matter what the process is, whether it's inverse norm or normal CDF, you're really just going to hit second and bars right away to start this off. So let's go through this again and just see how it goes. So immediately on the calculator, type second bars. It brings up a long list of probability functions. The one we want is option number 3 for inverse norm. I put that down. Oh, no, I didn't put that down. Let's put it down right here. So first thing we'll do is, after hitting second bars, go right, oh, clipboard, not sure why there's a clipboard there. Go over here to option number 3, and that's the one we have to hit enter on. Hitting enter on option number 3, it just wants 3 different inputs. It needs an area, a mean, and a standard deviation. So we go back up to our display, and the area that we used is 3.07. So let's type that in. I said 3.07. I need to get that right. 0.307. I'll start with the decimal place. 0.307. Then for mu, we often have to change these. In this problem, it is 0, so we're in luck. But the standard deviation is 10 on this one. So we input a 10. And that's pretty much our entirety of step 3, filling in the information. Yeah.
Calculator, like your standard deviation, there's like a thing that says tail and then left center right. Is that for this? Would that just be left? It
would be left, yeah. So this tail right here. In most people's calculators, you'll never actually see that, and it only accepts area to the left for most calculators. But you can buy a TI-84 that's something like maybe Silver Edition or CE Plus. There's lots of versions of this TI-84. Some of them format the screen just a little bit differently. So I'm always going to deal with the area to the left because I'm forced to. But in your calculator, you have options. You could have used the area to the right. If you want to match up our work, then yeah, you can always keep it area to the left. Other questions so far? Okay, thanks for mentioning that. There's actually another issue with calculators that was brought to my attention at the last part of class. Some people's calculators, even if it's a TI-84, it's going to look like this. You could still hit second bars, go to inverse norm, and this is all you see in some TI-84s. I believe there's at least one person in class that has a calculator that goes like that. Anyone else that sees the screen after hitting option 3? Gotcha. So I'll put extra advice on here if this is what we're looking at on all the notes. So here, this is what it should look like for our standard TI-84. But if we have, for option, I'm thinking of down here. For this particular problem or calculator, we first put in the area 0.307, so 0.307. And this is kind of strange. We need to put in a comma right after that. So the comma is right here above the number 7. Then put the value 2. So whichever calculator you're using, I'm always going to number these to say which order to put in the information. So input 2 is going to be 0 for the mean. Put in another comma, and then input 3 will be 10. Then all we have to do is close the parentheses, and it should look like this, a negative 5.04. Is that the value that folks are getting so far? Is that working out in your calculator, Marlon? Oh, that is odd. That is really close, though. Do you mind if I take a look on that, just to see how it's going? Oh, I think I remember this. So let's go back to second bars. Inverse norm. So 307, comma, then option 2 is 0. And another comma.
Oh, okay. I understand.
And then 10.
Yeah, okay.
So it should come out like that. Anyone else getting a value that's close or different from this negative 5.04? Awesome. So if you have this value here, then we're in really great shape. Really, the reason we're taking quite a while before even looking at example 2 on these notes is this is pretty pivotal. We know how aggressive web design is with rounding and decimal values and such. So if we can't get this just right, this whole section is going to be a struggle. It's best to take more time than rush through it. So we should get a negative 5.04. It'll look like this in a TI-83 or some TI-84s. Let's take a screenshot of this one as well then. So for step 3 in the TI-83 calculator, it looks like this. And for the right TI-84, it'll also look like that as well. Let's do it for the TI-84, just so we have 2 different options here. Wish you could open two at once, but I don't think it lets you do that. So for the T94, same kind of process. It just organizes the information so we don't have to comma separate and we know what's what. It'll look like this. So second bars, once again, hit option 3. Area to the left is the point, 307. Mu is 0, sigma is 10. And that's what the input should look like in this calculator. Okay, so whatever version we're working on, input the information like this or like that down below. Once the information is correct, we just hit, oh, I messed that up. Just hit enter right where it says paste. And notice this calculator, even the TI-84, it really is putting the information in this way. I just paste the function in with all the information thrown in the correct order. So one way or another, it all looks the same. It's just that the updated TI-84s have that extra window to organize all the information for us. So let me put it in here, enter one more time. And this is the final step, step 4 for success. Let me put extra space there. So once we get here, what we solved was we were trying to find the value or the solution to probability x less k equal to, and I forget the value, let me peek at it, 0.307. But we've in fact found it. It's right here and right here. So that's the k value, the missing value we needed. We can now say k equals negative 5.04. That's kind of wild. This is probably the weirdest equation solving we've seen in this entire course. It's a k inside of a probability function. The calculator knows just how to invert that and solve for k. So k has to be negative 5.04. Any questions at all, folks, with these warm-up problems here so far? Okay, so dealing with the normal distributions is pretty much the picture right here. That's why we liked the empirical rule and we took all that time to draw the pictures on quizzes and on exams, because all this stuff comes right back. And now we have to do it again, organizing information, so we can know what actually goes into the calculator and in what correct order. So let's now try out the problems down below. At this stage of the notes, we're pretty much in position of doing problems that look exactly like the quiz number, I forget what number that is, quiz number 9. We're up to 9 of them, wow. So quiz number 9, if we open it and take a peek, it gives us a scenario that we have to take a look at. This is one we've seen before, but we're going to analyze it with a calculator. It also gives us an x value to define what x will be relevant to the problem. And, well, it's just a standard kind of problem. It says calculate this probability, include a graph, we'll round to 4 decimal places. And this one wants a practical interpretation. We'll see some of those problems as well. I believe that'll be on example 3 for us. So essentially what we're doing is quiz problems at this point, which means those are the typical exam problems as well. Think of WebAssign as our opportunity to practice all this information. The quiz problems are pretty much an exam dress rehearsal, since those are the common problems. And lecture notes problems, those are really just to help us get through the quizzes, so we'll be in good shape for the exams. So here's how this one starts off. It tells us a machine that cuts corks for wine bottles operates in a way that the distribution of diameter of the corks produced is well approximated by the normal distribution with a mean of 3 centimeters, standard deviation of 0.1 centimeters, and X will denote the diameter of those corks. So that's the situation so far. It's quite a lot of information, even in this one sentence. And the first thing I would do is read it once and then read it twice. On the second reading, have an eye for what are the statistics or what are the population characteristics in the problem. They tell us here, there's going to be a mean of 3 centimeters and a standard deviation of 0.1 centimeters. They didn't say this came from a sample in any way, so these are more likely to be population characteristics. So what I would use here next, before I even start the problem, is put this on your scratch paper, maybe margin of the actual quiz or exam paper, and write out mu equals 3 centimeters. If you wrote x bar equals 3 centimeters, that would have been okay as well. I think this is the better description of this problem, since there's no information that this was a sample. They're saying this is what the machine is supposed to do. Its population average must be at 3 centimeters. And its population standard deviation, which we indicate with this symbol sigma, is 0.1 centimeters. We also have this right here. They told us X is going to be the diameter of quarks in centimeters. And so that's going to be relative for each one of the questions that we ask. We'll deal with X some way, somehow. Now that we've broken down the problem, pulled out some information from it, here's what the question starts to read. The specifications of the wine bottle call for quarks with diameters between 2.9 and 3.1 centimeters. So that's good information. We want to know what proportion of quarks produced by this machine will have the required diameter. Now, if it says what proportion, or if it says what percent, or if it says what is the probability, we're doing the same exact thing each and every way. So from that second sentence, I would probably just immediately write probability. We're going to find a probability as a proportion. Quarks produced by this machine have the required diameter. That's just saying X, which is the diameter of those quarks, is between 2.9 centimeters and 3.1 centimeters. So we have a probability statement. Now at least we know what we're about to solve. Next thing we want to do is, instructions will always say include a graph, same as with the quiz and same as an exam question. Let's highlight that in yellow since it's something to definitely not miss. And the reason I asked this right here for part of the question is, well, it's really our strategy. Without a graph, unless you practice these a lot, it's really hard to know what is really going into the calculator and what the correct order would really look like. Also, by including a graph, even if you made a mistake on the computation, my ability to award partial credit really comes through the graph. If I see that there's a slight mistake on the graph, but then you did put it in the calculator correctly, got a value out, you only lose a small amount of points just on the graph, and that's it. You don't have double jeopardy. So the first thing I'm going to do is draw a graph. It doesn't have to be a really high effort one like we did on exam 2, where we're using the empirical rule and saying what the rule would predict. Really, we're just putting as much information on the graph as we need to know what goes in the calculator. So I'll start with kind of a shoddy normal curve, but it'll do the job. And the center is 3, and it's often a good idea to put that value down. In fact, every time I draw a graph, I'd probably always do this for the notes. So those are the 2 population characteristics. Once we have the graph, there's still more that has to go on here, a good amount more. We go back to the question. X, well, X is on this axis here. It's the quark length. And we said X had to be between 2.9 and 3.1 centimeters. So it should be about between here, here's the 2.9, and about here, here's the 3.1. Now, the new thing that's happening here is probabilities are now areas under the curve. It'll be the area as X starts at 2.9, moves to the right, and ends at 3.1. So in other words, we want to know this area right here. Whatever it equals, that's the answer to this question. Well, any questions or comments, folks, so far? I guess I have a weird question. Even though we can't use the empirical rule anymore, we could still estimate the answer by having some expectations by the empirical rule. At 3, that's the mean. At 3.1, I've added a standard deviation, and at 2.9, I've subtracted a standard deviation. So that should be about 68% of the data, as per the empirical rule. The trouble is we can't use that value any longer. Web-aside, as well as on quizzes and exams, we're expecting something more accurate than the value of 68%. So here's how it's going to go in the calculator. Yeah, go ahead.
In the graph, is it going to be negative?
A negative number on the left? Yes, absolutely. This graph is wild because it actually goes to the left forever, unstopping. Other questions so far? Okay, so for what's going in the graph, Here's the order in either calculator. First, we'll put in this value. It's indicated as lower in the TID4 because it's the lower bound where the area starts, right at this fence here. 3.1, that'll be input number 2, and that's upper for upper bound. That's where the area stops in this location. Then finally, mu is input 3, sigma is input 4, and this function that we'll have to use will be normal CDF. Use normal CDF. Reason we're using normal CDF is, well, the actual proportion right here is missing, and that's what this function gives. Any questions at all so far, folks? Okay, so that's pretty much our graph. Push it up here. Okay, gotcha. And once we have our graph in, here's what it looks like in this calculator. We pretty much hit second bars to start off, go to option number 2, normal CDF, then just put in the values in the order indicated. So the lower value is at 2.9, upper value is at 3.1. The value of mu, that's right here in the center, but it's also written above the graph. That came in as 3 centimeters and sigma is 0.1. So altogether, our input should look like this before we get a value out. Hit enter on this screen, enter again, and that's our answer right there. Now in WebAssign, only in WebAssign, we do have to be really careful about rounding. This is asking for 4 decimal places of accuracy, and the 4th place is a 6. To the right is an 8, so we'll round up to 0.6827 on this problem. So 0.6827. I'll put this in a box just to indicate that was the proportion that they were going for. If we thought of this as a percentage, we would have said 68.27% of all the corks produced by this machine will have diameter between 2.9 and 3.1 centimeters. Probably didn't ask for a practical interpretation, so it's not required to write it down. In fact, the question is the interpretation on this one here. Well, how's that look to folks? Are we all getting 0.6827 so far? Yeah. It went kind of like this. On this calculator, I go second bars, option 2. My question for you is, do you see this screen? Or does it look like a bunch of words? It's got that screen there. Gotcha. On the notes in orange, I'll be doing this for each one of these problems. I'm just pretty much putting in the order everything is going in. So lower is 2.9, upper is 3.1, mu is 3, and sigma is 0.1. So with all those values in, your screen should look like this. And you just hit enter on paste. So hitting enter here gives me this as the output. Yeah, you have to hit enter on the paste, then you have to hit enter again once it pastes the function, then you finally get the number. Is that coming out okay for you? Okay, awesome. Anyone else having any issues getting that number out? Okay, awesome, glad to hear that. And just for the sake of the recording, I think everyone is doing pretty good with these, but if anyone has a slightly more old school calculator and it might be watching later on, this is what you would do in that calculator. So here is the good old TI-83. Its screen is blurrier, even though it's emulated. I don't know what that's about, but we'll live with it. And the TI-83 hits second bars. You still go down to option number 2. It's still normal CDF problem. It prints out the function. And now, if you use this calculator, pay attention to the 1, 2, 3, 4. Again, I'm going to put this on every problem as a guide of how to get through it. So it'll be at 2.9. You have to literally put in a comma, so that's what you get for getting a TI-83, but you did save money. This is like a $90 calculator, so there's some value in that, I suppose. For input 2, it's a 3.1. Hit your comma again, then 3 centimeters for the mean, comma one more time, 0.1 centimeters for the deviation, and finally close a parenthesis, and we have the same number, 0.6827 after rounding. So it looks like this in this particular calculator. Either way we do it, we have about 68%. That's what the empirical rule would say. But we get this extra precision right here if we do it exactly. Depending on that context, you know, that precision might be a really big deal. If you're making wine, this could be millions of dollars in revenue, being just a little bit less accurate, potentially. But we did it, folks. That's a full-on problem right there. This one was different since we had area between. That question first.
How would you write practical?
I would probably go about like this. And this is pretty much where chapter 5 is helping us out because it's identical to chapter 5. Start right here and we'll say 68.27% of corks produced by this machine. The reason I said corks produced by this machine is because that's what X was defined to be. X is the diameter of the corks. So I'll say corks produced by this machine is between a diameter of 2.9 centimeters and 3.1 centimeters. And that would be our interpretation on this one. Other questions so far? Awesome. Well, let's try this out again. Part B says, a cork produced by this machine that has a diameter smaller than 2.9 centimeters or larger than 3.1 centimeters is considered defective. You can imagine how devastating that would be. If your cork is too small, the wine is just going to leak out. Too big, it's probably going to leak out worse. It's never going to fit. And we want to know what proportion of corks produced by this machine are considered defective, and we'll include a graph to get that answer. This one's kind of silly in a certain sense that we actually don't need the calculator for this one. This one is more of a reminder of a formula that's still on the table for us, which is really, really helpful. It goes like this. Probability of an event A, any event A, is always 1 minus the probability of that event complement. So we found the probability that X is between 2.9 and 3.1. Let's draw that out again as a graph. So right here in the center is 3. Use 3 centimeters. Sigma is 0.1 centimeters. We still have a question that's dealing with the 2.9 centimeters and the 3.1 centimeters. So I'll put it here. Here's 2.9. And here is about 3.1. X is still the cork length. And the last question told us the area right here in the middle is 0.6827. We can just carry that to our diagram right here. 0.6827. So we have the central area all together. We just wonder, what is this area? So the area in orange is the one that we actually want. Anyone know what the trick might be to get it in one shot?
One is subtracted by 0.68.
Exactly. That's the idea with this formula right here. It's all about that 1. The total area under this black curve is exactly 1 as well. And so we can say the probability, or what are they saying? Smaller than 2.9, we'd be right here. X less 2.9 centimeters. Or, I'll write this as a literal or. You could use a union symbol if you like. It says larger than 3.1 centimeters. That means we're here by the red dot. And in the function, we could write X bigger than 3.1 centimeters. But then, like you said, by the empirical rule, this is just going to be, by the complement rule, this is 1 minus probability that 2.9 centimeters less than X less than 3.1 centimeters. So it's 1 minus 0.6827. Here's the 1 minus in the complement rule this time. And if that's all you put, 1 minus 0.6827 and calculate a value, that would have been just fine as well. These extra steps are just showing the process and how it connects to that old formula. Probability of A is 1 minus probability of A complement. So back in our calculator, all we really have to do is go let me try again. That was already a mistake. 1 minus, well, might help if we look right here where we're about to calculate, 0.6827 and we get 0.3173. So without even using the fancy normal CDF function in the calculator, we can get to a result directly if we notice the question here is complement to the question down here. And remember, complement just says the part that completes the whole. This is the part up here that completes the whole down right here. Any questions at all, folks, on getting that probability there? Okay, this one again was kind of a silly one where we could have worked really, really hard to get it through, but if we thought in terms of total area is 1 under the curve, we have area of one piece, just take 1 minus that area and solve the problem. But I don't think we're going to have any shortcuts on part C. We're going to have to work this one out directly. If you think about the problems that we did on quizzes or an exam question with the empirical rule, there's always a percentile type of question, and that's this one right here. So I'll put it down on the next page so we can have ample space to work on this. Let's try this out all over again. Pretty much every problem is going to say somewhere, include a graph. I will always highlight it, but this is new for the instructions, so let's highlight it this time. I'm just redoing the graph that we had above. Again, they're pretty low effort graphs. This might be the worst one for today, but that's okay. It's just organizing information. The center here is 3. Use 3 centimeters. Sigma is 0.1 centimeters. And this is X, which is quark length. Okay, so that's not the completed graph, but that's pretty much the graph we're using for any question in this problem now. It asks us, what quark sizes describe the 1% of largest diameter quarks produced by this machine? So here's what I would start off. I want to solve probability. X goes here. The thing that we're trying to find, let's give that one a special color. K, I'm going to put right here. And they also gave us an actual probability this time. Anyone see what the probability is that would go right here by the red dot? Exactly. If you have this right here, it would be a 0.01. Good call. So we take the percentage, convert it to an actual probability amount, and this is what it looks like so far. So it says what quark sizes? That's X. X is the quark length, diameter. Describe the 1%. 1% is here. Of the largest diameter of quarks produced by this machine. Only thing I haven't taken into account to put something right here is where we said largest. When it says largest, should we use a symbol like this, greater than, or a symbol like this, less than?
A rather than the large one, or would it be less than?
Turns out it wouldn't be less than on this one. It should be this one right here. But honestly, that is really tricky. Let's write out the reason why we put this one here. If you go X and that symbol, think the alligator eating the morsel of food, that's always a great way to think about it. We're saying X is larger, or another way to say is X is to the right. That's the larger part of K. So that's also telling us the direction we have to shade. Wherever we place K on this diagram, we'll be shading to the right where X would lie. So it takes some time to build all this. We want the curve here to organize the information. This sentence was really fast, but there's a lot of moving parts. It's good to take your time with this. And the next thing I want to place is the location of K. If there's 1%, then it's either going to be on the far left or it's going to be on the far right. And on this kind of problem, if we make a mistake, as long as you put the center of 3 right here, it's a very fixable kind of mistake. So let's maybe do something kind of, I was going to say silly, but maybe we should leave this to the class. Any volunteers on where K should go? Should be to the far right or to the far left? It's kind of tricky still, right? But here's what I would do. Sorry, say again.
If X is larger, it would need to be to right of A for K to be left.
That's a good way to think about it. If we put K, say, here, then I like the way you're reasoning through this. X has to be to the right of K, so X is somewhere in this location. But then the shading goes to the right, and so would the probability value. So if we go this route, then we just have too small of a probability in this location, where we say X is to the right of K. But honestly, this is pretty much how this all works out. We just have to put it somewhere, read through the problem and see if it makes sense. Here, the point one should really be to the left if it was in this picture. And so for that reason, I would change it up like this. We put it, say, right here. Oh, that's the wrong color. Let me try again. We put it right here into the far right. Then we're saying X is to the right of K. So we are shading in this location. Not too much to shade there. But in the probability statement, it's saying probability that X is to the right of K is 0.1. That means this 0.1, 0.01 goes right here on the very far right. And that's a diagram that does seem to make a lot of sense. There's not too much area right here. K is to the very far right. And we're looking for what K value is going to give us 0.01 area to the right of K in this location. X is being to the right just means we're shading to the right there. So our diagram is just about there, but we need one extra thing. In most people's calculators, this isn't true for every single calculator. Say, for example, some people might be able to say area to the far right. But in most calculators, we only are able to use the area to the very far left. So I'll put here 0.99. Does that make sense on the 0.99 in that location? Essentially, it's the complement rule once again, like we did above here. If you know area of one segment, take 1 minus the area, you have it for another segment. Here, if they give you 0.1, but your calculator only deals with area to the left, you have to use that area. So let's put this in the notes very carefully. I'll call this input 1 area. And let's put a statement down below here as well. Most calculators, I'm thinking TI-84s when I say that, only deal with area to the left. So that becomes basically a mantra for us. Every time you see this problem, I'll always say, but we need the area to the left, even if we put something to the right like this. So that's our input number 1 into the calculator. Really, that's the hardest thing about a percentile style question is getting the area just right. Then input number 2 is this one. Input number 3 is this one. Mu and sigma are always the last things to go in, always in that order, the mean and then the standard deviation. So now we're about ready to put it into the calculator. But I did mention one thing. Even if we made a mistake on the diagram here, you'll be able to tell right away, especially if you put the center of 3 in this location. So I'll do it the right way first. Or actually, you know what? Let's mess it up first. Please don't copy this down in the notes. Just to show what does it look like if we make a mistake and how do we tell? Sometimes that's the most important thing here. So this is the approach where a mistake will happen. And it would go like this. We start out with second bars. We're on the right track here. Now, we're not going to use normal CDF in this problem. Reason being is we already have the probability. We need to use inverse norm because what we need is the value right here. In fact, let's just pause and say use inverse norm. With that directed arrow, that's the reason we don't have the K value. So once we go to that option, now if I saw 0.1 and I never made a diagram, let's cover it up, I'd be tempted to just put 0.1 in the calculator because that's the value I see. So let's do it. This is the mistake right here. So that's not going to come out correctly, but it's good to know when a mistake occurs so we can detect it. On this problem, the mean, I do have to peek after all, mean is 3, standard deviation is 0.1. Well, yes, 0.1. So that's the information going in. If I hit enter on all this, here's what the K value comes out as, a 2.7674 after rounding. But that's not the right value. And honestly, if this is all that's on my paper, I have no idea why it's not correct until I look at the graph. If K is 2.7, it can't be there. All the values to the right of 3 are larger than 3. So that tells me right away, oh, I made a silly mistake. I found a K value to the far left when I wanted it to the far right. That just means we'll reconvene, go back to the drawing board on this, hit second bars, back to inverse norm. That was the problem. It always has to be area to the left to get the right value out in this particular calculator. Again, if you have a fancier one, you can control area to the right and grab the 0.1, but I'll always show area to the left since that satisfies most calculators. So now area is 0.99, mu is 3, sigma is 0.1. Hit enter on all these, and here's our new value. This one says to round to 2 decimal places, which makes sense. This isn't a probability. This is just an ordinary measurement, and those quarks were rounded to one decimal place. So our value for K is 3.23 centimeters. K equals 3.23 centimeters in this problem. What a weird way to solve an equation, right? But it's not a normal equation, so we have to do some strange process to make it happen. Any questions, folks, on getting this right value out? Is everyone getting a 3.23? Yeah, go ahead.
So just to verify, like with the calculator, when we're dealing with something that has to do with K, then we're using the inverse norm. But when we're not doing with K, it's normal
Normal CDF, yeah, exactly. You could think of it in these terms right here, or maybe just down the problems we're working with are fine. If the question is missing a probability, you need normal CDF. So normal CDF gives the probabilities. But if the question is missing the value on the x-axis, that's when we're using inverse norm. You know what? In fact, that's a good thing to write down right here. For probability, x less than 5. And there's lots of ways to write this. It could be x greater than 5, x between 3 and 5, and so on. But for all these kinds of questions, where the probability is unknown, use normal CDF. And it's this right here that's causing us to use normal CDF. We just don't know the probability. For any question that goes like this, for probability x less than k, again, it could be greater than k, just depends on the problem. If they give you a value, maybe 0.37, then this right here, this is the whole reason you would use inverse norm. It's because you have the probability, and you're trying to reverse engineer what value of k gives that probability. So here, use INV, standing for inverse norm. And inverse is really the right statement to make here, because if you look at both of these problems, they are inverted. If you're missing the probability, that means you have the value on the x-axis. If you have the probability, it means you're missing the value on the x-axis. So it's in that way these are inverted to one and another. But that's pretty much the cheat sheet. The thing that makes this section tough is you can change the information here. X could be less than, greater than, between two elements, and so on. You can change the information here. And it just gives us way too many scenarios to say, always do this in your calculator for this problem. Instead, the safest thing to do is just put down a graph each time. Then the more you do this, the faster it is to produce that graph, and the faster it is to put in the values into the calculator. Well, any last questions, folks, on getting through this one? Okay, well, for our problem we have down below, I think example 3 is definitely going to be a little bit too long for us to get through in about 4 minutes and some change. So we might call it a day here just a few minutes early. that sound all right to everyone? Okay, any last questions then to call it a day? Okay, well, have a great night, everyone. If you do have questions, I'll be available down here. When we come back on Thursday, we'll be finishing off these notes and we'll be in this section next. Once I get back to the right spot. We'll be next in section or in chapter 8. So we're skipping around. We're now pretty much only grabbing the topics we need to do a confidence interval procedure and a hypothesis test procedure. That's exciting. That means we're on the second half of the course, inferential statistics. But somehow, some way, the normal distribution is what you need, even if your data is categorical. That's really kind of weird. Well, have a great night, folks, and I'll see you all on Thursday.